Handling of missing data is a very important part of data mining. There are two solutions that typically are used. The first one is done when the number of records having missing values is relatively small. And when that happens, a simple omission of the missing record is all that needs to take place. This can be problematic, however, if there are a large number of values that are missing, because then that can introduce some bias into the models that are used. The other thing that can be done is imputation, where the missing values are replaced with some sort of reasonable estimate or substitute. One thing that we are going to do quite a bit of is normalization or standardizing of data. There are several ways to do this, but the basic idea behind it is getting two variables or two or more variables onto an even level playing field. And doing this allows you to compare, say, apples to oranges, dogs to cats, horses to chickens, and so forth, by subtracting the mean and dividing by the standard deviation. And that's the function that's used most often. But there are other ways of normalizing data, including putting it on a 0-1 scale by subtracting the minimum and dividing by the range. The big problem that we run into with data mining, however, is that of overfitting. And this is something that really needs to be dealt with, because the statistical models that are used can become very complex, and when they contain lots and lots of variables and lots of parameters, it turns out that you can get a very good fit to the data. But the problem arises when that fit is too good, and instead of fitting the signal in the data, oftentimes the noise in the data is also fit on top of that, which is something that we want to avoid, because when new data is brought in and used on the model, the noise tends to drive the prediction, which can lead to very poor performance. An example of this can be seen here with these 7 data points comparing expenditure to revenue. The relationship depicted by this line is that of some sort of polynomial, and you can see that the line perfectly intersects with all of the data points, which is not very realistic, especially if you wanted to go and make a prediction going into the future. So for example, if you had expenditures of 700, according to this line, this would be your estimate. Well, that really doesn't show the overall relationship. In fact, there's quite a deviation from what you might think is a better relationship, a more simple relationship that comes from having this line. And really what's going on with overfitting is this distance right here, which would be the error if we use the simpler model, is now being attributed to the relationship between expenditure and revenue, which for prediction purposes really is not a good idea. The causes of overfitting are generally too many predictor variables, or too many parameters in our model, or too many models. Try lots and lots of different models, you tend to find one that fits really well. And that's one of the criticisms that is oftentimes levied towards data mining. So something that we want to be careful with. How do we deal with that? Well, there's an ingenious method for doing that, and this is the real reason that you're in this course, to learn how to do this without overfitting. And the process that's done in data mining is to take your data, split it into 2 or 3 subsets, call one a training partition, one a validation partition, and potentially a test partition as well. But the training data is the one that's used to build the models. All the models are built on the training data, whether it's regression or neural networks or classification trees or whatever the model is that you're using, you do that on the training data. And that allows the models to be built, but it also allows for there to be overfitting done. And so the next step is to take the models that were built on the training partition and apply the validation data to those models and come up with a score. And what happens is, since the validation data is a completely different data set than the training data and was not used to come up with the parameters, the validation data set tends to expose when there is overfitting that's been done by the training data. And so the error that shows up in the validation data set will typically be bigger than the training data set. And that's okay. In fact, that's good because it tells us that the model we used was overfit. So let's do an example of this by looking at one of the data sets from the text. In the what's called the West Roxborough Housing Data Set. This is data collected in 2014 in Boston. And you can see there's a number of variables here, total value, tax, so forth. And the idea is to predict the total value of the house based on these other variables. And you can see a list of the variables here and a description of what they all are. And so total value is going to be the y variable. If we were going to do a linear regression model, think back to when you took introductory statistics. This is just a simple linear regression model that has the y value as total value, and the x's are made up of a collection of those other variables. So we would go into the JMP data set and make what we call a validation column. And don't worry about if you don't know how to do that right now. You will very soon find out how to do this, and you'll be doing this all the time in this course. So here we're splitting the training set as 50%, and a validation set is also 50%. And there's no test set, but we could specify that. Notice there's 5,802 values. That's for each of the variables that we just looked at. And once we have a validation set, then we can run the regression model. Here we would put in as our y variable, total value, and validation. We tell it which variable to use for the partition, and then the x variables, we would throw all of those in here. We'll talk more about how to pick the best model later on when we talk about linear regression in a few weeks. But then you would just click the run button, and then in the output, when you see the response total value, you click the little red triangle and then save the columns, the prediction formula and the prediction values. There's lots of other things that you see that you can save, and so here they're suggesting that we save the prediction formula and the residuals. And so then in this additional output, we have all of our variables, and then we have two new columns, predicted formula and residual value. So according to the model that we would use, what we see here for the first observation is a total value of 344.2 thousand, predicted value of 383.93, and the residual on that is negative $39.73 thousand. And so we want to know how good our model does at fitting, and unlike what we did with regular statistics when you took your introductory stat course, either as an undergraduate or high school or in graduate school, what we're really interested in is prediction and how well our model does predicting on the validation set. And so usually in the training set you can get very small errors, but if you overfit your model, then you're going to be fitting error, and so we want to avoid doing that. So here's some of the output. We look at, these are the residuals, so the average residual on the training set is very small. The average residual on the validation set is also very small. If we look at the root average square error, which is oftentimes known also as the root mean square error, we see that these things are fairly similar. Now, the mean residuals we would expect to be very small, and that's not going to necessarily be a good measure of the variation or the error. Instead, in the cross-validation section here, we see that average, so the root mean square error, and we'll talk more about that later on. But these things are fairly close to each other, which suggests that our model is not necessarily overfit. So how do these things, how are they calculated, the root mean square error and or the root average square error? Well, the error is the actual value minus the predicted value, so you might call this y minus y hat, and another way to think of that is the residual. And so the root mean square error says square that, add it up, take the square root. And generally, root mean square error and average error are going to be more informative than total error, just for that reason. Sometimes the partitions are different sizes, and so you're adding up more numbers, so one should naturally be bigger than the other, even if the averages are the same. So in summary, we have two different methods, or subgroupings of methods, supervised and unsupervised methods, and we're going to be learning about both of those in this class. Supervised methods have to do usually with making predictions, either classification, which would be a 0-1 scale, and or prediction where we get an actual number that we're coming up with. But we also will look at supervised methods, or sorry, unsupervised methods, where we want to simplify and summarize the information contained in a data set in a certain way. And before we can do any of these methods, though, we oftentimes are going to need to pre-process the data, clean up the data, make it so that it's going to work with the algorithms that we're doing. Once we do that, we want to avoid overfitting, and so we're going to use the partitioning notion with a training set and a validation set, and sometimes we'll use a test set as well. Again, the idea here is that you don't want to fit noise, and the reason for that is because noise is attributed to randomness, and randomness is something that cannot be predicted by definition, and so we oftentimes run into problems by trying to do that, and we really don't want to do that. And so then finally what we're going to do is use the models that we come up with that have the best performance on the validation data set, and then use that to score or make predictions for newly obtained data, and make decisions based on that. So that's the end of this video. Check the folder, the week 1 folder, for a couple other videos, and we'll see you then.